The topic of this lecture will be the structure and acidity of alkynes. Alkynes are molecules that contain carbon-carbon triple bonds, the simplest of which is ethyne. The triple bond requires 2 pi bonds, requiring 2 free p orbitals on each carbon, meaning that each of the carbons involved in the triple bond are sp hybridized. Let's look at the orbital drawing for this molecule. Each of the carbons has 2 unhybridized p orbitals, one in the plane of the picture, and one going into and coming out of the plane of the picture. These 2 sets of p orbitals form the 2 pi bonds of the carbon-carbon triple bond, one in the plane of the picture, and one in front of and behind the axis between the 2 carbons. The carbons also have 2 sp orbitals each. One of the sp orbitals from each carbon form the sigma bond between the 2 carbons. The other sp orbital on each carbon forms the sigma bond to the hydrogens. Due to the sp hybridization of the carbons involved in a triple bond, the protons attached to an alkyne are acidic. This is because an atom that holds its electrons in an s orbital is more electronegative than an atom that holds its electrons in a p orbital. This has to do with what these 2 orbitals look like. An s orbital has its electron density focused around the nucleus, while a p orbital has the electron density further away from the nucleus, with very little electron density near the nucleus. What this means is that electrons that are held in a p orbital are held less tightly, less close to the nucleus, and electrons that are held in an s orbital are held much more close to the nucleus. Therefore, as we increase the amount of s character that makes up the hybridized orbitals around an atom, it holds its electrons more tightly. In other words, the atom is more electronegative, and it pulls the electron density away from the hydrogen, making it much easier to be abstracted. We can see this when we compare the acidity of different alkanes. For example, let's compare ethane, ethene, and ethyne with the acidity of their protons. In ethane, carbon and hydrogen are connected together using the sp3 hybrid orbitals of the carbon. These hybrid orbitals are 25% s and 75% p. In ethene, the carbon uses sp2 orbitals to bind to the hydrogen. These carbons' hybrid orbitals only contain 33% s character. In ethyne, the carbons are sp hybridized. These hybrid orbitals are 50% s character and 50% p character. What we see as the percent s character increases is that the pKa decreases. Remember that a smaller pKa means we have a stronger acid. In other words, it's easier to deprotonate the molecule. The pKa of ethane is 50. This makes ethane a very weak acid. For comparison, acetic acid has a pKa of 4.75, and hydrochloric acid has a pKa of -7. These are considerably stronger acids than ethane. As we increase the S character in ethene, we see that the pKa is reduced to 44. Still a very weak acid, but slightly less weak than ethane. The pKa of ethyne is 25. This is considerably more acidic than either of the other molecules, because the S character in these carbons is 50%, effectively making these carbons more electronegative and easier to deprotonate. Another way to think about this is to look at the strength of the conjugate bases. The conjugate bases of each of these acids is shown. As we increase the S character and the carbon becomes more electronegative, it's better able to stabilize the charge. Therefore, the conjugate base of ethyne is going to be the weakest base, meaning that ethyne is going to be the strongest acid. Terminal alkynes are the stronger acids than any other hydrocarbon, but they're still very weak. That means they need a very strong base to deprotonate them. Remember that the pKa of ethyne, or terminal alkynes in general, is about 25. In order to deprotonate an alkyne, we need a molecule that wants to be protonated even more than an alkyne, which means that its conjugate acid needs to have a larger pKa than the alkyne. Bases that we typically think of as strong, such as hydroxide ion, are not strong enough to deprotonate an alkyne. The conjugate acid of hydroxide ion is water, whose pKa is 16. Typically, the very strong base that is used to deprotonate an alkyne is called sodium amide. In solution, sodium amide dissociates to give sodium ion and NH2-. The conjugate acid is ammonia, whose pKa is 35. Therefore, sodium amide is a strong enough base to deprotonate an alkyne. This produces a carbanion, a negatively charged carbon. More specifically, we call this an acetylide ion, when the carbanion is on a carbon of a triple bond. If our base was sodium amide, we produce the sodium salt of the acetylide ion, which can be used in further synthesis. One last important point is that in order to be deprotonated, the alkyne must be terminal. An alkyne that is not terminal, in other words, an alkyne that is in the middle of a molecule, will not have any protons and therefore cannot be deprotonated to form the acetylide ion.